Hi, I'm Derrick Stacey, the product owner for ACOPOStrak in North America at B&R Industrial Automation. And for me, automation is flexibility.
Welcome to today's episode of This is Automation. Today we've got a very special guest with us, Derrick Stacey. So hello, Derrick.
How's it going?
Going very good. We're here at the B&R Roswell office at 7 a.m. so that there's no noise here. But if you hear some noise towards the end of the episode, that's probably because people are starting to show up to work. So, Derrick, before we get started talking about ACOPOStrak, tell me a little bit about yourself and what your history is with B&R.
Sure. So my background is from mechanical engineering, but I sort of stumbled into automation from my last company. I did like linear actuators and ball screw and belt driven systems, and they needed some motors to drive them for a trade show exhibition. And so, got trained up on B&R components and hardware to do that, and then was like, man, this is actually kind of cool. Mm-hmm. And then all of a sudden, B&R does this boot camp where they train you from zero to an automation engineer. And so that's sort of how I got started in this. And so I've been with B&R now for 5 years and worked a little bit with R&D and now sort of moved on to the product side. I got to spend a lot of time in Austria at the beginning, but it's been very, very cool so far. And, I was happy enough to work for B&R that I bought myself a bright orange suit to really represent B&R.
Yeah, that was Automation Con 2018, right?
Yeah. The first and only time it's left the closet. It's very difficult to find the right occasion.
Yeah, the right occasion
for orange, but maybe Halloween.
Yeah, there you go. So, what is it that you do now?
So I work on like I said, on the product side for product management here.
Okay.
For North America, which means I'm responsible for dealing between sales and R&D and trying to make sure customers enjoy the products they're working with.
Mm-hmm. So I guess that means that you spend a good bit of time with our customers, specifically focused on ACOPOStrak?
Yes.
Okay.
Yep. So anytime that there's someone who's trying to get introduced to it or is trying to sort of figure out for them how does it work best.
Okay.
We bring the product knowledge, they have to bring the process knowledge, but I think together we really can find some unique solutions.
Okay, good. So I guess before we start talking in too much detail about ACOPOStrak, I wanted to kind of give a quick intro that we give sometimes to customers. So there's a thing that we like to talk about called the SCurve of Innovation. So this is basically where we're talking about, what's the difference between disruptive technology and the sustaining technology. And usually the people that are innovating those two things are not the same people, right?
Yes.
So, the difference here is really new market players are the ones with disruptive technology, and then the incumbent market players are just trying to sustain what they have. And so this is kind of ripped off from a Guy Kawasaki talk, and he talks about jumping the curve. So how do you get from, the S-curve of innovation from 1.0 to 2.0 to 3.0, and so on and so forth. So that what I thought a really good example that he gives is in the ice industry. So ice 1.0 is harvesting ice, right? So we've got these big frozen lakes, and we go out and literally dig up the ice, and then buy horse and buggy, take it into town, right? So the way that you innovate there is you get more horses, you get a sharper saw, you get a bigger saw, right? And you make it more efficient to harvest the ice. But to jump the curve to the next generation of ice technology, you're talking about like an ice factory. So a centralized location where we're actually manufacturing ice. And the people that are developing sharper saws are not the people developing ice factories.
It's also like location based, right?
Right.
Ice 101, you had to live near a lake. You had to have crazy harsh winters.
Yep.
Only people in northern Chicago could get ice.
Right. And nobody wants to live in northern Chicago.
Right. All the people down in Alabama, very difficult to get themselves ice.
Yeah.
So going to this more, manufacturing definitely helped spread it. So now like the benefits are definitely different for depending on where you live, and now everybody can get it. And a lot of it I think comes from, what do you see yourself as? Do you see yourself as a company that cuts ice out of lakes, or are you providing, temperature control to your customers. And I think that's the one thing that you see when you mention the new market players versus the incumbent people is I see myself as a refrigeration company, someone who controls temperature versus no, I just make blocks of ice and ship them out, or I cut blocks of ice.
Yep.
And so that's really sort of where we're seeing this for sure.
Right. Yeah. So, I mean, you mentioned like the difference between making ice and controlling temperature being like your core focus. So that's like kind of the ice 2.0, if we're sticking with that example, to 3.0, where now you've got people. You can everybody that's listening has, you know, an ice machine in their house or apartment, right? And again, the people that were building out those ice factories were focused on making ice and delivering ice and, you know, building bigger warehouses or whatever it may be. And then you've got new players that come in and they're like, well, why don't we just make an ice machine that's smaller and can fit in your house, right? So, and I guess, how do we translate this to ACOPOStrak? So what would you call like transport 1.0, 2.0, and then 3.0 is presumably this track technology? Exactly, yeah. So you look at it, it's like the classic picture of like the Fords walking off the line. You just have these mile-long conveyors where you've got one person putting on one component, and then it kind of rolls down to the next. And so that's sort of the line shaft, you know, long, massive conveyor. Everything runs at a fixed speed. And then I'd say like the next innovation from there is servo motion control. So now not is it mechanically linked. So your timing is going to be, you know, fixed gears and cams and hardware. It's going to be an electronic clock, right? Everything's going to be servo driven. So you're going to have some PLC or some PC that broadcasts, you know, time out to the individual pieces, and then they run at their own sort of speed of that time, but it's still sort of linked that way electronically. And then obviously now with track technology, we're trying to sort of break that apart and say, listen, you don't need this centralized time. Everybody's on their own thing, you know, cars on the street, right? I mean, we should because there's speed limits, but nobody drives, you know, at the same speed. And so we should allow for sort of that variability by giving everybody their own sort of, all right, I mean, you sort of have to follow your same path, right? Because it's a track. So you're not going to be able to get away from that. But everybody can pick their own speed based on what their needs are, right? I think that's probably the easiest parallel to see it is, you know, sort of a little bit more free-for-all than anything else today. Good. Awesome. So I'm excited to dive into that a little bit more, but I always like to dig into the history first. I think I'm a little bit of a history geek. So I don't know if you can tell me much about the history of ACOPOStrak because it's pretty new, but as far as track technology itself, I know there's some other players in that realm. We've got, you know, Jacobs Automation, which, you know, has now migrated to Rockwell.
That's right.
So I guess they got bought out in, when was that? 2015 or something like that. And then, you know, you've also got the MagnaMotion, which is now a Rockwell acquisition as well. So what can you tell me about the different players and kind of where they came from and how B&R fits into that picture?
A lot of it in the North American market was Jacobs Automation. And so they put together, you know, what's now known as the iTrack. And it was pretty innovative. I mean, you think about it, it was like each shuttle, each mover is its own servo. It was able to hold, you know, it still is quite a few pounds of payload. It's probably one of the higher payload systems on the market. It's a pretty heavy duty system as far as being able to sort of shove things around. But obviously starting from a small company and then getting bought by someone like Rockwell, you know, that transition period can be quite long, right? Because now you've got to adopt it and spread that knowledge to a much larger organization. And so I think right now they're finally sort of getting up to speed with it. Whereas the MagnaMotion side was built more for, you know, lab level, right? It was more about sort of puck moving, right? You could see from the design of their movers that it's meant for placing, you know, a plastic puck or some machined component on it to then place product in and nest it and be able to sort of shuttle them around. So the focus was, you know, couldn't be further one side to the other of sort of heavy metal, move things quick and fast and heavy around versus something where we kind of want to be a little more delicate and move things around a little bit more slowly. But those are two great examples of sort of what we're going to term like racetrack versus train yard. Racetrack being sort of a single continuous loop. It may not be an oval. It may, you know, differ from that, but it's going to be a single path. Whereas train yard, if you think about it, can be parallel paths. You know, when you pull up into the MARTA station or whatever, you can see there's multiple train stations, multiple paths, and then as it goes across, you've got all the switches and the branching from there, and that's something that they can take advantage of, being able to sort of deliver product to various different positions within a machine or between machines. And so that's sort of what we wanted to bridge between, is have a train yard style where we could have the flexibility and the shape definitions that you don't get from a single fixed path. But we needed to obviously be a little bit more powerful, a little bit heavier duty, only because, B&R traditionally does packaging, right? So we have to focus on, what packaging OEMs and what packaging machines sort of need. And we dialed it in very much around that mindset. I think we did a very good job.
Yeah, I think so.
But yeah, so we sort of piggyback on that. But we also piggybacked, the next piece is obviously ATS, our friends up in Canada. In fact, I was just there last week.
Good. So what does ATS do? How are they related to B&R?
Yeah, so ATS is automated tooling systems. So they are a line integrator for everything. Everything from medical devices to pharmaceutical to consumer electronics. They even do some power generation stuff, so they get involved. They've got like a nuclear and traditional fuels business as well. So they're quite large, and so they've utilized track technology, specifically the SuperTrak, which was their sort of internal competitor to the iTrack as far as shape and design and layout. But because it was totally used internally, the general market never got to see it. And so B&R was lucky enough that we partnered with them on their PCs, their hardware side, and was like, hey, guys, you're building your own computers. That's not really a sustainable business model for someone who isn't Intel or, Dell or whomever. And so with that, we sort of got plugged in with them, and that helped spur on a lot of this innovation because they held a lot of patents. And so we sort of piggybacked on their technology, a little bit different than the iTrack, because we utilize the permanent magnets a little bit more. So actually we don't grab onto any rails. We don't grab onto the track physically. We're sort of just smacked
stuck on
via magnetics.
Yeah, so this is a little bit of a tongue-in-cheek question, but what happens when you turn the power off? Do all the shuttles just fall off?
No, I mean they freewheel for sure, but no, they don't. They don't fall off, and that's
yes,
kind of a benefit, I think, in automation systems.
Good. So I guess now let's start talking about the nitty-gritty of ACOPOStrak, and I'm just curious, what is the like craziest pronunciation that you've gotten? Because I get a lot.
So I've had people sort of flounder about 3 letters in and just go, the track. We know what we're talking about. We're calling it the track. It's the B&R track. It's like, okay, that works for me. But what about yourself?
So I've heard APOCUS a lot.
Ooh.
ACOPOS. There's a lot of times where people just start with an A and then just a blur of sound comes out after that. So.
I mean, for everyone listening, it's spell ACOPOS.
Yes.
Track.
And the correct pronunciation is ACOPOS. So yeah, the first time actually that I heard about ACOPOStrak, I was in Austria, and we had met with one of the sales guys who was over there for something else, and he was like, "Oh, have you seen this new ACOPOStrak stuff?" And I was like, "Oh no, what is that? Tell me about it." But I thought he said OctopusTrak. And so for like 6 months after, because I didn't hear anything else about it, I was like, OctopusTrak, that's such a weird name, but all right, let's see. So we've got this running joke in the Southeast team now that there's an OctopusTrak in development, and it's like a SuperTrak or ACOPOStrak with like really high payloads, and then there's an articulated arm robot and 8 shuttles. So you've got like 8 robots flying around on the track, and that's your octopus. Yeah. So just some ideas that you can pitch to R&D.
The next application I see that could use that many robots.
Yeah.
I feel like I'm just going to draw it out exactly like that.
I mean, that's whatever happens, right?
It makes me think of the carnival ride.
Yeah. Good. So, okay, we got the name out of the way. So just tell me what ACOPOStrak is a long stator linear motor. Is that the right terminology?
Yes, LLM.
Okay.
For sure.
So tell me what that is. Let's assume I know how a servo motor works, so we don't need to talk about all the electromagnetics of it. But just, tell me how that translates.
Essentially, we just take a standard servo and cut down one side and laid it out flat. And so, excuse me, the rotor becomes sort of the shuttle, so the mover. So instead of having a 3-phase rotary movement, we take a single phase for the permanent magnet, and then we're just moving it and sliding it back and forth along the stator. So each of the coils, as we actuate them, sort of pulls the permanent magnet around via the magnetic field. It sounds pretty easy as far as that, but obviously if it was easy, then a lot more companies would be doing it. But there's a lot of nuance to it, but it's pretty standard technology. I mean, for us, we sort of encapsulated it with our current standard technologies, right? Our standard drive is controlling it, no different than it would a stepper motor or servo motor or whatever, from our ACOPOS micro family. So it's really the accumulation of standard technologies just in a different form factor.
Okay, cool. So you mentioned there's shuttles and track segments. What else makes up an ACOPOStrak, and how do all those things kind of play together from a mechanical standpoint, and then also the electrical control side of things?
So the last piece is really the rails, right? So we actually do it as B&R. We love our 3-piece. I don't know if you talk about explaining, but we love our 3-piece design. And so the rails, just like you would think from a roller coaster, are on the top and the bottom, or left and right side, and then the thrust is placed in the middle, so the magnetic push, and then the shuttles are essentially the cars. So they just set on it with a couple of wheels, and that's the basic mechanical system. And I'm sorry, what was the rest of the...
So the mechanical side, that sounds good. Yeah. And then on the electrical side, control side, what is that architecture?
Gotcha. So we use an enclosed encoder signal. So each one of the track segments, so each one of the pieces that build up a track, we sort of do it like a Lego, where we've got 4 different shapes that we then can turn into any other loops and curves and things of that nature. Obviously, it's a little difficult. I'm waving with my hands, but really not getting much to anyone listening. And so, we were able to hand off this magnetic field from segment to segment. So it's each shuttle is controlled individually by a single or 2, 3 coils on each individual track segment, like the motor block. But then because of its very nature, the long stator part is we just put the stator next to another stator, and then we can handle that transition. So essentially we can have an infinite track as long as we had enough power for that. This thing could go for miles, and that's sort of the novelty of it is you're not fixed to a rotary period. You're not fixed to sort of a stroke length, because linear motors have been around for quite a while, but they always have end stops, right? You've got 800 millimeters of stroke or whatever. This is infinite, and we're expecting for you to be able to put 100 or more of these individual motors side by side, and they're all about just over a half meter long, so you can have fairly sizable travel.
Okay, so 100 segments. How many shuttles?
We're talking 200, 300. Hopefully, it's more. It's not a limitation that we've run into quite yet. I assume it's going to be something probably not on the hardware side, but on the PC.
And I just did want to jump back real quick. So you're saying as the shuttles move across 2 segments, there's something happening in the software firmware side of things that's handling the transition. Yeah. Is that similar to what happens when we're going through a diversion? So going from one track segment to an adjacent track segment?
Yeah, we use the magnetic field and as the sort of the encoder signal, so we can feel where a shuttle is based on the magnets. Okay, and then very quickly we've got power link. So our real-time deterministic field bus is able to talk very quickly between any 2 segments, whether they're side by side or parallel, and then use, especially when they're parallel, use like a field weakening to actually just sort of nudge the magnetic field across. It's kind of cool, but very, very simple, as we just, make one side feel 20 newtons more pull force than the other side. So it sort of just casually jumps
over
across. Yeah.
Good. So you mentioned 100 meters and 200 to 300 shuttles. That sounds like a lot. Is that a typical application to have that much track and that many shuttles? Or could you just tell me, like, what is a normal architecture? Is there a normal architecture?
I don't think that there's something that I would consider normal. Obviously, people like to think in loops because that's sort of just standard technology. So rotary dials, conveyance systems, they all sort of lend themselves to the start and the finish are the same place. But we're trying to get people to think a little bit outside that box. So can we, flip the track on its side and be able to have one straight where you're doing a process and then a return area underneath. So you take your oval and flip it up on its side. But our hope is that no, we never get into a normal. We want to find some optimal ones. So we're constantly playing in Visio and doing all sorts of drawings and trying this, trying that. Does it fit for floor space? But recently, the last few have all been loops, just traditional stuff, but being able to use the varying space between shuttles to make the most advantage to use it versus, say, a standard conveyor or rotary dial.
So let's, I guess, dig into that a little bit more since you just mentioned it. So I guess oftentimes, like when I talk to people about ACOPOStrak, the first thing they're thinking is, oh, this is a really cool way to move things around my plant. But that's not really the right application, right? So what is the right application and what is the wrong, we'll say, application?
Yeah, so if it has to move, just fast or long distances, probably not it, because there's no control really necessary there. If you're just sort of dropping it on a shuttle and then sending it off and forgetting it, probably not the best use of it. But if you've got something that doesn't have to be about size, but it's about the variation in how a product needs to move. Or the various different places it needs to get to. So if that can be something that's software driven, where day one, maybe we're doing ice cream just as a nice example. So we're feeding strawberry in, and at some point, we finish baking strawberry and we want to put on vanilla. And so, that's standard packaging, that's standard production is one flavor at a time. But now, say we've got a plant where we've got 3 or 4 lines and they're all just doing different flavors. But I don't know, some marketing person decides, hey, this month it's Neapolitan, is the chocolate, vanilla, strawberry. Say we want to do a Neapolitan pack. So now you've got chocolate, vanilla, strawberry, and you feed them all into the same packaging machine at total random and let the system decide, right? Normally to do that, you'd have, maybe 10 or 20 or 30 people taking packages of the individual flavors, ripping them open and sort of placing them all by hand to make these packs. Well, the goal is to get something that's flexible, and that's what the track brings you, is that flexibility. And that's really the most optimal solution for it. Is you've got different flavors that you want, different outputs. Maybe you want to throw in, okay, we've got all this, but we want to do maybe 2 chocolates and a vanilla just because that's something that someone ordered, right? Say from a cell phone, you put in, hey, I want this to be my ice cream pack, and then it spits that out for you. And that's the sort of flexibility. Obviously, it wouldn't be an individual ordering it, but it could be, say, the corporate ordering system that spits these out. And that would be sort of the ideal case. But it's all about flexibility in the output of the machine, whether it's a mix of different types or if it's something where you want to be able to, at any one time, just change on the fly. And that's the big thing is we don't think about things like that right now. And I think that's where we're sort of in education mode is, long run, single item batches. Fine if it works for you, but there's going to be a case, or maybe there's a different revenue stream available to you by going to these smaller order quantities, going to these customized things. You may not do, tens of millions of units, but as a company, the flexibility of orders that you're probably saying no to because you don't have that flexibility, that is something that essentially you're just throwing away previously, and now you can actually take that in-house. And instead of paying, just to keep with the ice cream thing, like someone like a co-packer, someone that you just pay where I'm going to send you product, you're going to rip it open, you're going to make whatever I tell you to be the packaging, and then ship it off to our customers. And so that would be obviously that would be best case scenario for the use of track technology.
Okay, good. And that sounds like it might be kind of hard to program. You've got each shuttle, you've got to program each shuttle. Is that?
Yes, exactly. No, actually not.
Yes, no.
we program each shuttle, but it's not like we have to maintain control of that from say the operator or the programmer side from start to finish.
Okay.
And I guess that's sort of where you were leading me, and I got lost there for a sec. But we actually do it more like path planning. So it's more like GPS. We know at any one point where a shuttle is. We know where it needs to go. And because it's sort of a closed system, we can draw a line from A to B.
Okay.
And then just release it. And it sort of meanders its way. And if anyone gets in its way, it'll slow down and wait its turn, very patiently. And then when an obstacle or another shuttle gets out of its way, it speeds back up and goes on its way. And that's sort of takes a lot of the pressure off of a programmer, because if you've got to deal with every set position, every sort of collision point in the system, it becomes very tedious. And our goal is to take a lot of that off you as the programmer, and sort of just say, all right, sort of fire and forget. You're going there. Good luck to you. Yeah. I'll see you when you get back. There. Yeah, exactly. Yeah. So really, it'll raise its hand when it gets to where it's at, and that's the only ones you have to deal with. So you're not dealing with all of them at any one time. You may only be dealing with maybe 10%, if that, in the program at any one time. So we write everything to be very modular and localized, where it's like, I call it amnesic, right? Shuttle shows up, you know everything about it, you talk to it, it walks away, and you've already forgotten about it. And then the new shows up, oh, hey. Then you talk to it, you deal with it, and send it off, and you've already forgotten about it. And that's the sort of the way that you have to deal with it. You want to deal with it with localized points versus looking at it as a system. Because as you mentioned, big, lots of shuttles. If you talk about machines with 200 servo axes, people go, blah.
Yeah. So you mentioned something kind of in that discussion where you're talking about collision avoidance. So that's something that I was actually talking to someone the other day, and he had some experience on another track system. He was like, yeah, I just don't know about this stuff, because he's like, last time we worked with this, you have no idea how many of these things I just like exploded into each other. So, making a small mistake, and you could easily do that. What happens on an ACOPOStrak if you, let's say, like try to intentionally cause a collision, or is that possible? Like what
No,
happens?
From our standpoint, we pre-calculate the whole path, right? We don't actually calculate all of the movements inside of it, but we say, all right, here's your path. Here's A to B. If at any point in time, once the first shuttle starts moving, if you send a shuttle from B to A, they actually both come to a stop, because the path that the second shuttle from B to A was drawn intersects with the first shuttle. And so then they'll both come to a stop and say, collision deadlock. So it actually knows pretty early on what's going on. And so, we tell people, it's like, listen, the only way to get two shuttles to crash is to turn the system off and to sort of bang them together by hand, because the system itself keeps track of, every shuttle to the left and right of each individual shuttle. So it knows its neighbors. It looks left, it looks right, and then sort of travels along to keep in mind that, we could be carrying EpiPens or some sort of expensive medical device on this, and so we don't want these things bashing into each other. Not
right.
Maybe if it was all like ho-hos or cupcakes or whatever, we would be a little more comfortable with that.
I don't know. I don't want to get my ho-hos all smashed in the box. Oh man. Okay. Good. So I guess one of the things that we do a lot is simulation with these ACOPOStrak systems. So can you just talk about what do we mean when we say simulation A, and then kind of like what do you expect people to get out of a simulation? Is it just an animation? What do you really expect people to use this for?
Yeah, it's a useful animation. So obviously when you think animation, you think cartoons, and really that's what it is. All we're doing is visualizing how the track is going to run. So we have all the set points, because we have, the drives simulated inside of the laptop. And then all they're doing is just following sort of XY coordinates. So if you drew it out as a 2D system, it'd be you're just looking from the top down and you're watching the shuttles sort of move around a fixed path. But from that, we can get all sorts of really good information. So without having to build any hardware, without having to really take a lot of time, in less than a week, we can see where our bottlenecks are. We can actually optimize the throughput of any one station or the system as a whole, just by varying the number of shuttles on a system, the speeds, the accelerations, what we call the multi-up. So, a single shuttle getting worked on is 1 up, 2 shuttles getting worked on at the same time would be 2 up. That's sort of the nomenclature. Mm-hmm. And so by varying the number of shuttles being worked on at any one time in any station, we can sort of affect the bottlenecks. And most of the time, if you're talking to end users and people who do line integration, they're chasing bottlenecks. Is how do we improve one piece to open up that bottleneck to then find the next one? And we want to be able to sort of design it. It's like, okay, pick where your mechanical bottleneck or your machine bottleneck is, and then let's pre-design the system to really keep that one full, and then let the rest of the system manage itself based off of whatever that trickle output is.
Right.
And that's something that's hugely important that not a lot of other people sort of can show you very early on in the process for you to make, engineering decisions before you've actually designed a system. I mean, the track tends to be the backbone, right? It's the main transport layer. And so having that sort of defined, then all you're doing is just like plugging modules on, whether it's a printer or labeler or whatever. You're just, it keeps it very modular. And that's the goal is we can sort of get out of all of the other machines' way by doing our work early and saying, all right, this is what we're going to deliver to you and this is how it's going to work. And I've actually, proven that out on all of these demos and machines that we've worked on is, we get hardware like less than 2 weeks before it needs to ship out. And so 99% of your effort is done on a simulated environment, and then it's just sort of download the program, cross your fingers, close your eyes, and as long as you don't hear any loud noises, then it's like, okay, there we go.
And so that's, I guess, one of the really powerful things about the simulation is it is the machine code.
Exactly,
right?
Yeah. Super high fidelity with what's actually going on. And so it's not like you're doing double work, right? The minute you create a simulation, you actually have a starter project for what your machine could be.
Okay.
And so, that could be huge. I mean, obviously we talk about moving quicker, right? Not just the product, but also the design cycle. And that is definitely a leg up on the design cycle as far as how fast you can get to market with this sort of thing. Is if you can do most of it just casually, before you design it or before you build it, that obviously gets you further down. So your commissioning period is much shorter because a lot of the issues that you're going to run into, maybe you can say, oh, you know what? Turns out that would be a bottleneck. So here, let me adjust the speeds of the rest of the line and the other places to sort of meet my bottleneck. And if that's meet your throughput needs, boom.
We talked about simulation. We've talked about the mechanics of the system, the electrical parts, the control. I feel like we've kind of talked about ACOPOStrak as it is today. So what can you share with us as far as what's coming in the future? Anything that's not confidential? Is there anything that you can, tell us what to keep an eye out for?
There's a couple things. So on our roadmap, obviously, like I said earlier, packaging is big, but also beverages. So we need to be able to live near and in systems that do bottling and sort of handle food. So we have to be able to be washed down. So having an IP69K, so a caustic washdown variant is absolutely crucial for us going forward. So that's going to be something where it's going to be just a gleaming mass of stainless steel. Just very, very shiny. I cannot wait to get some shuttles in to be able to see what they're going to look like. The other thing is obviously on the safety side, B&R has a whole safe motion control suite of things to be able to have people interact with press heads and servos and things like that nature in a safe manner, and being able to add that to the track means that we can have operators interacting with the track in one part while a piece on the other side is moving at full production speed. And so really being able to do changeover on the fly or maintenance on the fly can be pretty crucial for uptime. OEE. And then the other, I guess the last piece is looking at, what Optima showed So if you look up the Optima ACOPOStrak demo, they integrated a flex link or some plastic chain conveyor with ACOPOStrak, and we're able to hand off shuttles and receive shuttles back on ACOPOStrak. And so that's obviously for as we talked about those long runs, that's a great way to do it, is you put something that's sort of a well-known quantity that can handle, changes in elevation. So you sort of just run it up to the ceiling, and then it sort of kind of finds its way eventually overhead and out of the way of the rest of the system. And that's a lot of how end users, design their plants anyway, as you've got sort of first floor, second floor, third floor, and third floor is mostly about just getting things to and fro.
So any other insights there?
The basics, right? Interaction with robots. Obviously, that's going to be a big one is how do we, and I can't wait for us to maybe be, I don't know, not the first, but maybe one of the first to get a cobot and have it interact. I mean, that's going to be a big thing. Obviously, with the ABB acquisition, we now got a lot of really cool robots in our product family. And so, the mobile robots. So imagine having a robot on wheels sort of drive itself up and act like an operator for a little bit. That's something that I think is going to be, a little bit on the R&D side, but it could be vital for sort of these flexible lines. I mean, we talk about flexibility, and if you could have a robot drive itself up, park next to the track, interact with either the shuttles or the product itself. And then once its job is done, or maybe where it's needed more somewhere else, sort of just goes, all right, uncouples from it and drives itself away. I mean, we're talking like Jetsons level stuff here right now, but it's there. All the pieces are there. And now it's just someone brave enough to pull it off. Right.
Yeah. That's awesome. So it sounds like there's a lot of cool stuff coming down the pipeline. There's a lot of cool stuff already out, so I'm excited to see some applications as they start rolling out here.
Yeah, people are starting to, spin up on it a little bit, get a little bit of traction. It's definitely a totally different way of thinking. So I'm super excited to see what some people, come up with, because now that we're sort of releasing it to the general public, now you got a lot more people with a lot more ideas. Right. And so I have a feeling that's, here, so we're going to see some really cool uses of it.
Awesome. Well, thank you so much, Derrick. I appreciate you taking some time to talk with us about ACOPOStrak.
No, thank you. Much appreciated. This has been great.
Well, if you want to reach Derrick, I'll give you his personal cell phone number. I'm just kidding.
It's on my business card, so
No, so I guess in the future episodes, we're going to be talking about some more exciting stuff. We'll be talking about more ACOPOStrak. I've got a conversation lined up with Dave Emery, who's the Director of Sales for Track Technology at B&R. We'll talk about SuperTrak, IoT, machine learning, lots of cool stuff on the schedule. So super excited about that. If you're an Apple Podcast or Spotify user, make sure you follow us, subscribe on there. And if you enjoyed the podcast, make sure you leave a comment on LinkedIn or on Apple Podcast. If you need to get in touch with me, or if you have a special request or idea for the show, you can pass that along to me directly through LinkedIn or, of course, by email. You can reach me at automationpodcast@gmail.com. As always, this episode was sponsored by B&R. So Derrick and I are both B&R employees, so sponsored by B&R in more than one ways. But, in between episodes, if there's anything that you want to learn, make sure you check out the B&R website and the B&R YouTube channel. There's lots of really good content on there. So thanks for listening, and we'll see you next time on This is Automation.